so we're going to talk about sampling distributions and what that means. But first, let's think about stuff that we do know and distributions that we do know. And we're going to focus on normal distributions. And so we know that, well, really what we're going to talk about is population distributions. So let's say we were given, for example, the average height of men is 5'9", 69 inches, with a standard deviation of maybe 4 inches. I think it's more like 3 inches. We'll go with 4 inches. All right, population distributions represent every individual in the population is represented on this curve as individuals, right? So we're looking at this curve, and in the middle, we see that the average is 69 inches, so most individuals will be 69 inches tall, 5'9", but there will be some variation. So you might get, it varies. Most people will be within 4 inches of that average. So most people will be within 6'1" to 5'5". So most guys will be between there, individual guys. And then we'll just widen it up a bit. 95% of guys will be between 6 foot, is that 6? And 5'1", 95% of guys, pretty much all guys will be between that. And then 99.7%, so literally all guys will be between 6'10" and 54, 57, and 4 something, right? So pretty much all guys will be between there. There might be a couple guys that are really tall here and a couple guys that are shorter than 4 feet, like technical midgets there, or dwarfs. And so this is our distribution for every individual in the population, okay? And it has a spread of about 4 inches. Now, we also know what sample distributions are. That's what we do in class all the time. We just take a look at a small sample and we look at every individual in the sample. Okay, we do that all the time. Let's say we're looking at a group of 30 students, group of 30 men, and plot that distribution. Okay, and typically what we see is the sample distribution looks pretty much the same as the population distribution, though, with 30 people, it's not going to look exactly the same. But most guys, if we take a random group of 30 Americans, most guys will be about 5'9". You'll have a few that are 5'8". You'll have a few that are 6 feet, etc. Right? So you'll see kind of like this going on. You'll have like a couple that are pretty short. And you probably won't see that wide of a spread as you see up here. But you'll see something like that, and then it will take on a shape very similar. All right, you probably won't see these guys out here because it's very unlikely to get people who are out here above 2 standard deviations away from the mean or below 2 standard deviations away from the mean. So most of your sample will be within 2 standard deviations away from the mean, but it should take a similar shape. All right, so these are sample distributions. They represent every individual in the sample, whereas population distributions represent every individual in the population. Now, what we're going to talk about is sampling distributions. So what that represents is actually a distribution of samples of a given size. So it's either going to be we'll Well, let's look at the average. It's going to be some statistic, the average or the percent of a sample, and then every possible sample average or percent in the population is on this curve. What do I mean by that? Well, that would be like saying, okay, instead of looking at every individual height, what I'm going to look at is I'm going to take a sample of 3 guys. So here I was just looking at an individual compared to an individual. This was like one dude, right? This was also one guy. Each dot represented one guy. Now what I'm going to do is I'm going to take a sample of 3 guys. All right. And so let's say one of them is 69 inches tall, one of them is, I don't know, 65 inches tall, and one of them is 6 feet, right? That would be probably a decent guess for a group. And what I'm going to do is I'm going to take the average of that group. So this is 68.6. So even though we had a short guy and a tall guy and a medium guy, when I look at that average, that is what I'm plotting on the curve. And notice that it pretty much is right in the middle. And so what we do is we take every possible sample of 3 guys, and that's what I plot on this curve. And what we find is that the center remains the same. But if you think about it, the standard deviation, how much a group of guys, their average, compares to another average, is probably going to be a lot smaller than just comparing the individuals. Like we can even see within this small sample, the individual comparison here is 7 inches. But then if I were to take another 3 guys, we could make it something within here. So like maybe 62 and 72 and 66. This is 66.6. The difference in the averages is only 2 inches, whereas when we look at the individuals, the difference is much larger. So the spread of averages is going to be a lot smaller. So the spread decreases. Okay, and that makes sense because we're going to be looking at a sample, and when we start to group them, and we get closer and closer to the population, so there shouldn't be a lot of spread away from your center for the population. So the spread will decrease because you're grouping it closer to what's true about the population. Okay, so the center stays the same and the spread might decrease. I don't know by how much yet. Well, I do know because I know the formula, but we'll get to that eventually. But the spread, instead of being 4 inches, it's probably going to be closer to 2 inches. So the averages, if I look at a group of 3 guys, it's very, very unlikely that they will average less than 5'3". Whereas if I was looking at one guy, it's way more likely to find one dude who is 5'3" than find the average height of 3 guys being 5'3", right? Okay, so this is a sampling distribution. So the sampling distribution is looking at samples and how the samples are distributed. All right, and you might be asking yourself, well, Ms. Shine, what do you mean by of a percent? This is all quantitative data. How do we deal with categorical data? Well, with categorical data, we're going to start looking at percents. the nitty gritty here. So let's say we're looking at, I don't know, in the population of high school students, today, I should have Googled this before, but let's say, I'm gonna Google it now, so I'm gonna pause the video. Okay, I wanted to look up the percent that go to trade school, but it was too difficult to find. I did find the percent that go to college. So in the population of high school students today, about 70% go to college. Doesn't mean they graduate from college, but they go to college. Okay, so if I look at Pritzker, which typically has about 95% go to college. They say it's 100%. 100% get into college, but about 95% actually go in the fall. So typically has about 95% go to college in the fall. Are we unusual? Okay, so how do we understand if that is an unusual amount? So unusual being more than 2 standard deviations above average. Okay, so in a sampling distribution, we saw that a sample pretty much mimics the population. So in a sampling distribution, your population percent, you would assume that all samples or most samples would show, like if I took a group of, let's say, in this case we're looking at 240. I think there's 240 or so of you guys. So if I were to take a group of 240 kids, what percent would I think are going to college? Well, I would assume that it's the same as the population, 70% or 0.70. Because most samples will look like the population, right? Like if I ask you, if I took a sample of, I don't know, 200 kids and 68% of them said they were going to college, I would assume that the population is similar to that, right? If it's a representative sample. So that's a good thought here. Our sample must be representative. Okay, so it must be random. And technically, you guys are not a random sample of high school students. But we're trying to see if we are rare compared to random samples of high school students. So we're looking at a bunch of random samples of high school students. Okay, we also must be big enough to make this a normal distribution. And to check for big enough, we do, it's based off of binomial probability, but we check that our sample times the P, this is P, population proportion. We check that N times P, which is, that has to be bigger than, that could be wrong, 68, is bigger than 10, and that very much is. And then N times Q, Q being 1 minus P, like we did in binomial probability. Okay, and that also has to be bigger than 10, which it is, and that way we know that it's big enough to create a normal curve, big enough to represent our population, okay? And then the last thing is we check for independence. Okay, we can't have one person affecting another. and we can't have the samples affecting each other either. We need to make sure that our sample is small enough compared to the population so that we're not using fractions. We're okay using these decimals. And this is true. Oftentimes, your population won't be given in numbers. You'll just have to write it out. Like, we don't know how many high school students or high school seniors there are in the U.S. I think there's like, I bet there's like, I don't know, like 4 million. And so we know just based off of an estimate that 240 is less than 10% of like 4 million people. So we're good to go. So with that, we can make this normal curve. And we have to figure out what that spread is. And it's, again, based off of binomial probability, and I can show you a proof if you're interested. But the formula for the spread of a sampling distribution is the square root of the PQ over N. Notice that your sample is involved in the spread, which we saw earlier. We saw that our spread decreases when we look at a sample. So as our sample increases, spread decreases. Okay, and you can think about that numerically. As your denominator gets bigger and bigger, that number gets smaller and smaller. Okay, you can also think about it conceptually. As your sample gets bigger and bigger, you're closer and closer to what's true about the population. So you're getting narrower and narrower towards the true population. Okay, so we're going to calculate that here. And we just type that all in at once. 0.0295. So basically 0.03. Like I would say 0.029, but then I need to round up, it's 0.030. So 0.73, 0.76, 0.79, 0.67, 0.64, 0.61. Okay, and so the question is 95% unusually high? Well, yes, 95% is unusually high because it's more than 2 standard deviations above the mean. Okay, we can actually figure out what is the probability of getting 95% to college of 240 students. So 95% is somewhere way out here, and I want 95% or more. So if I think about that, I drew a line here. We know that on normal curves, when I draw this line, that represents a z-score. And so we're really just finding a z-score here. All right, we take our value, this line represented 0.95, minus the center, how far away from the center are we? And then how many standard deviations is that? Standard deviation was 0.03. And so our z-score is 8.33. We are 8.33 standard deviations above the mean. And then to find that probability, to go from a z-score to a probability, I normal CDF. And I should get basically 0. There's like no chance that I could be 8 standard deviations above the mean. So I'll do it anyway. Second vars, normal CDF. 4.08 times 10 to the negative 17th. 4.09, sorry. All right, so there is 0 chance that we could get this high of a college matriculation rate. So we are pretty fantastic as a school. Though when we start looking at our retention rate and like how many students stay in college, we're pretty much on par, though we want to see that increase. I think we're above average still, just not as unusually high. We're not 8 standard deviations away from the mean. We're probably closer to 1. Okay, so these are sampling distributions. I'm going to give you another one. Your first step is always to determine, 1, can you make a normal curve? And then 2, you make your normal curve. And then that includes finding your standard deviation. And then 3, you start to answer this question with a z-score and normal CDF. Okay, so let's do one more problem, and then we will be done. So, start a new page. Let's say in the population, I don't know, 30% of homes own at least one dog. In your block, there are 30 homes. What is the probability over, actually let's make it 50. I don't know how many are on a block. Let's see. We probably have what, 1, 2, 3. I think we're close to 40. 40 homes. What is the probability over, I don't know, let's say over 15 homes have dogs? It could be under 15, whatever. I'm just saying over because it's easier to think about. Okay, pause the video and try this on your own. You want to 1, check conditions. Those 3 things there we had, which were random, big enough, and independent. And then you want to make your normal curve. And then you want to find that z-score and normal CDF. Pause that video and try it yourself. Okay. First thing, our n here, our sample size is this 40 homes. Okay, and we'll just say, we can assume that like my block is just a random group of 40 like families. So 40 homes. So we assume it's random. Technically, it's not super random. I'm like in a certain area, and in my area, most people are Hispanic, and I don't know, do Hispanics have dogs more often than not? I don't know. So we would just have to understand that a little bit more. But for now, I'm gonna assume it's random. Let's see what else I got. I think it's really the age range that kind of determines if you have a dog, you know. So maybe it has to do with the age of the people in my block, but okay, so I assume it's a random sample. I make sure it's big enough for normal. By checking n times p, and that's bigger than 10, and n times q, which is 1 minus p. Which is, what, 28, so that's bigger than 10 as well. So we are big enough for normal. For normal approximations, we can make a normal curve. And then we need to check for independence. Right, so one home having a dog does not affect another. Just because I have a dog doesn't mean my neighbor across the street is gonna have a dog, right? And that's Avriel. Okay, so one home does not affect another, and we need to make sure that we have a small enough sample compared to the population. The population is Chicago homes. Chicago homes. right? And that's definitely true. So we're good to go. We can make our normal curve. In the middle of our normal curve, we would assume that the percent of homes in my block is the same as Chicago, which is 30%, because most samples will show 30% of homes have a dog, but there is going to be some variation because not all samples are the same. And we check that variation by doing the square root of P times Q over N. .072. So this is 0.372, 0.444, 0.516, and then the other way, 0.228, 0.156, 0.084. Okay, so now the question is, what is the probability? So this was 2, here's our checking conditions, here's our making our curve, and our last step is to find that probability. So what is the probability over 15 homes have dogs? Over 15 homes out of the 40 have dogs. So the first thing is, these are all proportions. So I need to make this into a proportion. 15 out of 40. That's 0.375. So I'm right here. So the question is, what is the probability out of 40, 15 or more have dogs? So this is my line is at 0.375. So I need to figure out how far away from the center that is, and then how many standard deviations it is. .042, and then I normal CDF to find that probability. Second VARS, normal CDF, 1.042999. So there's a 15% chance that over 15 homes have dogs in my neighborhood. Pretty good chance, all right? And this is sampling distributions.